Okay, Chapter 9, Section 3, Separable Equations. This chapter deals with differential equations. So let's take a second to think about what are differential equations, and then we'll come back and revisit specifically what are separable equations and how we can do the questions in this section. Consider the following example. Let's say that f of x, say y equals to f of x, which equals to x squared plus 3x, then its derivative could be written as y prime, also written as f prime of x, and while we're at it, also written as dy dx, right? Lots of different notation styles to represent the first derivative, and all of them, of course, mean that this is 2x plus 3. Okay, so now if I think about evaluating these guys when x equals to 1, let's see, that means that f of 1 is going to be equal to 1 squared plus 3 times 1, which gives me 4. And f prime of 1 is going to be equal to 2 times 1 plus 3, which equals to 5. Okay, so now what I'm going to do is I'm going to come up with an equation that involves the variables and these various values. So, for example, I might come up with something like this. How about y plus x times, say, 4, right? So when x equals to 1, we know, of course, well, that would mean that x is 1, so that one's 1. When x equals to 1, that would be f of 1. F of 1 would be a 4, so that would be a 4 belongs there. So this would be, at x equals to 1, this would be 5 times 4 makes it 20. And then on the other side of the equal sign, I could make it a y prime. First derivative, that would be a 5 times a y. Okay, so I have, this guy is, when f prime, this is going to be a 5, and this guy is a 4. Right, so from here, when x equals to 1, y equals to 4, f of 1 equals to 4, that's where this guy's coming from there. And when x equals to 1, the first derivative is equal to 5. This guy, that's where this guy's coming from. And, well, likewise, the 4 from here, that's the y. And x was 1. So what I have here is a true statement, because then I have that when x equals to 4, I'll have 4 times 4 plus 1 equals to 5 times 4. And so 20 equals 20, it makes it a true statement. Okay, so I've created a nice true statement, and now I'm going to take this guy, and I'm going to distribute it a little bit, mix it up. This will be equal to 4y plus 4x equals to y prime y. And just to make it a little bit more fun, I can just move things around a little. Let's move this on the other side. And so I end up with 4y equals to y prime y minus 4x. Okay, so what I've created here is an example of a differential equation. This is a example of a differential equation. Notice that, well, it's an equation, equals, and what's special about it is that not only does it have the variable y and the variable x, but it also has the first derivative of the function within it as one of the terms, right? So if you're given this, right, I was just kind of creating it here, but if you're given this, your mission would be to somehow reverse engineer this and figure out the value of y, the original function, right? So to solve it and figure out what this is over here. Good. That would be your goal, to figure out y equals to that. and maybe also figure out the first derivative, right? That guy. So that's your mission, to undo this process and figure it out. So some of them have solutions. The way I created here, I can see that when x equals to 1, I'm going to get a true statement. So that might be a valid solution. Some of them do not have a valid solution. And it might be, again, a goal to figure out the values that make it a true statement. Okay, so that in general is differential equations. Of course, that can lead to lots of super crazy, complicated equations. For example, you might run into equations that look like this. How about sine of x, y prime minus tangent of y prime times y divided by x minus 2y prime equals to y squared, times the square root of y prime. Ugly, right? So how can you possibly, undo this crazy knot of functions and eventually solve for y, get the equation of y, and figure out, of course, the derivative of y, of course, and also figure out values of x that make this a true statement, keeping in mind that maybe there is no solution, or maybe y cannot be expressed as a function of x. That's also a possibility, right? So all kinds of crazy, weird things can happen. The world of differential equations is massive, and people focus their entire educational path. You can get a PhD with a concentration of becoming a great differential equation solver, which is just really hard. Lucky for us, we're not going to deal with crazy, weird things like this. We're going to focus our attention on a very, very specific little group of differential equations that happen to fit a certain characteristic that actually make them pretty easy to solve. Okay, so that's what separable equations are. So what are separable equations? Okay, so separable equations. A separable equation is a first-order differential equation in which the expression for dy dx can be factored as a function of x times a function of y. In other words, it can be written in the form of dy dx equals to g of x times f of y. So the name separable comes from the fact that the expression on the right side can be separated into a function of x and a function of y. Good. So it's important that they're multiplied. Equivalently, if f of y does not equal to 0, we can rewrite it as dy dx equals to g of x over h of y, where the h of y is equal to 1 over f of y. To solve this equation, we can rewrite it in the differential form h of y times dy equals to g of x times dx. Good. So we can get all the y's, a function with all the y's on the left-hand side times dy equals to a function with all the x's times dx on the right-hand side. Then we integrate both sides of the equation. So we integrate both sides, and hopefully those are two integrals we can solve. So this equation, equation 2, defines y implicitly as a function of x. In some cases, we may be able to solve for y in terms of x. We can use the chain rule to justify this procedure. If h and g satisfy 2, then we can take the derivative of both sides. And so the derivative with respect to x of the integral of h of y dy is equal to the derivative with respect to y times derivative of y with respect to x by the chain rule. On the right-hand side, we know that the fundamental theorem of calculus says that these two kind of cancel each other out, and we end up with the g of x. And so these guys also kind of cancel out and give us a function with respect to y. And so we get back to the original statement. All right, let's look at an example. All right, so here are the exercises for section 9.3. Let's do a few of these. Let's start off with number 6. Okay, so let's begin by manipulating this so that it fits the form of a function in t times a function in u, right? Because those are the two variables we're working with here. So notice that we can rewrite this quite easily as du dt is equal to 1 plus t to the fourth power over 1 times, and then I can rewrite this guy this way, and I can factor out a t squared from the denominator, so it'll be a t squared there, times u plus u to the fourth power. And so therefore du dt can be rewritten as 1 plus t to the fourth power divided by t squared times, and this is 1 over u plus u to the fourth power. Good. So here is a function of t, some f of t function, whereas this is some g of t function, g of u function. Thus, we've satisfied the separable part of it, right? We were able to rewrite this as a multiplication. Good. So now what we can do is separate it. Let's put everything with u's on one side, everything with t's on the other side, times dt times du. So all we have to do is multiply both sides of this equal sign times the reciprocal of this. And so we can easily end with, or leads to, u plus u to the fourth power times du. So like all of this times du. Well, let's take a minute and write it down over here. This is going to be times u plus u to the fourth power on this side. That cancels with that. And then multiply this side by u plus u to the fourth power, like that. So then I have du dt is equal to 1 plus t to the fourth power divided by t to the second power. And now I multiply both sides of the equal sign by this dt. So that'll cancel with this and multiply it by this. I get that. And so now I end up with exactly what I wanted. The integral, so it's going to be u plus u to the fourth power du is equal to 1 plus, is equal to 1 plus t to the fourth power divided by t squared dt. Good. So this was a separable equation because I was able to do this. You're not always able to do this, right? As you can imagine, there are some questions that are presented in such a way that it's impossible to separate them. Okay, so now that we have it like this, what we could do is take the integral of both sides. So we're going to integrate this side, u plus u to the fourth power du, and integrate this side, integral of 1 plus t to the fourth power t squared dt. This should be nice and forward, nice straightforward, no problem. This I'm going to separate into two separate ones. So this will be integral of u plus u to the fourth power du. And this is going to be the integral of 1 over t squared dt plus the integral of, and then they reduce to give me just t squared dt. Good. Okay, so now these two are fairly simple integrals. This is going to be equal to 1/2 u to the second power plus 1/5 u to the fifth power is equal to, and this is going to be negative t to the negative 1 power plus 1/3 t to the third power. Right, let's double check. If I take derivatives, bring down the 2, cancels with the half, gives me that guy. Bring down the 5, cancels with 1/5, gives me that guy. Bring down the negative 1, that makes it positive. Subtract 1, I get to the minus 2, so that gives me this guy. Bring down the 3, subtract 1, I get that guy. Okay, so I was able to find it. Here is my equations. And now there's a... Okay, and then all we have to do now is think about the constants. Now, technically, every time we did an indefinite integral, every time we solved an indefinite integral, there would have been a constant added to it. So there would have been a plus constant on this side. Let's call it c sub 1. And then I did this in indefinite integral, so there'd be like a plus c sub 2. And then I did this indefinite integral, so there'd be a plus c sub 3. And now if I bring this one over and kind of brought them all together, I could say that this is equal to 1/2 u squared plus 1/5 u to the 5th equals to minus, let's write it as minus 1 over t plus 1/3 t to the 3rd. And then I'd have this plus the first constant plus the second constant, plus the second constant plus the third constant minus the first constant. But, the whole point of a plus c, of a constant, is that it's just some number, and, it doesn't really matter what it is. So all of these can just be written as a constant, right? Let's just leave these all as just a c, right? Where c equals to all of that. And that would be our final answer here. So 1/2 u to the 2nd plus 1/5 u to the 5th equals to negative 1 over t plus 1/3 t to the 3rd plus some constant c. Let me put in the plus c, and this is where c equals to c sub 2 plus c sub 3 minus c sub 1, technically. But, people just ignore all of that and just kind of assume all that to be true. And so I think in almost every case, you'll notice that people just don't include this at all. They don't really think about that at all. Kind of leave that all kind of omitted. And they just go, okay, well, whatever. There's plus some constant at the end. That's all that really matters. And so here is our final answer. Now, it would be nice, or the nicer ones are the ones where you can further solve for, say, u in terms of t. So if we can rewrite it as a function u equal to something in t's, like t to the 3rd minus t squared, something like that, where you're able to solve for it, would be nice. But that's not always the case, and this is one of those situations where you really can't solve for u. Right? There's no real good way to move forward. Can't solve for u. And for that matter, you can't solve for t either. So you're kind of stuck this way. Okay, so that's as good as it gets for this one. Let's try another one. Okay, let's try number 10. Okay, solve this differential equation, right? It's an equation, and it has derivatives inside the equation, so it's a differential equation. Our goal is to find z, to find dz dt, if we can. Let's see. So first of all, we got to use our algebra skills to manipulate this, so we can see if it's a separable differential equation. So moving this over to the other side, we can get that dz dt equals to negative e t to the plus z. And we know that adding exponents is the same thing as multiplying two exponential numbers with the same base. So dz dt is equal to negative 1. You can think of it that way. Negative 1 e to the t times e to the z. So now there's separable equations. Here we have a function of t. This is some f of t, function of t. And this is some function of z. Some function of z. So separable. And now I can solve, put all the terms that have a z on the left-hand side, all the terms that have a t on the right-hand side. So I'm going to multiply this side by 1 over e to the z. Multiply this side by 1 over e to the z. So we end up with e to the negative z dz, dz dt equals to negative 1 times e to the t. And now I'm going to multiply both sides by, just a stick to the color coordination. I should have left it as black. That's e to the negative z. And now I'm going to multiply both sides by dt. Multiply this side by dt. This guy cancels, this guy cancels. And so I'm left with e to the negative z dz equals to negative 1 e to the t dt. And now I'm ready to take the integral of both sides. So I'm going to integrate this side, e to the negative z dz equals to the integral of negative 1 e to the t dt. Okay, so the antiderivative of e to the negative z is going to be e to the negative z times negative 1. So the derivative of this is equal to that. Equals, and now the derivative of this, well, that's just going to be minus 1 e to the t plus a constant. Okay, so next I'm going to multiply both sides by negative 1. So let's copy it here. E to the minus z equals to negative 1 e to the t plus c. I'm going to multiply this side by a negative 1, multiply this side by a negative 1. So I'll end up with positive e to the negative z equals to e to the t minus c. Let me copy this up here. Continue. Copy this guy up here and say that this means that e to the negative z equals. So now if I apply the ln function of both sides of the equal sign, I get ln of e to the minus z equals to ln of e to the t minus c. This comes out in front. That's one of the beauties of a log function. So these two operations kind of undo each other, and this becomes minus z equals to ln of e to the t minus c. Multiplying both sides by negative 1, we get that z equals to negative 1 times ln of e to the t minus c. And finally, we know that we can bring this up here into the exponent of the argument of our log function. This becomes ln of, and then e to the t minus c raised to the negative 1 power, which means that z can be written as ln of 1 over e to the t minus c. And there's our answer. Okay, so let's try a new one. All right, let's try out number 14. Okay, number 14. X plus 3y squared, square root of x squared plus 1 times dy dx equals to 0. So this is the equation we're trying to solve. Don't let this confuse you. This is a boundary condition. This is additional information that's given so that we can isolate the value of c, that constant at the end. So we'll worry about this down the road. For now, our first task is to try and see if this qualifies as a separable differential equation. Is it possible to rewrite it, right? We ultimately want it to be rewritten in a form such that there is some sort of function in the variable y times dy equals to some sort of function in the variable x times dx. That's what we want to try and identify. Some function in y with no x's in it times dy, some function in x with no y's in it times dx. If we can do that, then this is a separable equation. Then we can integrate both sides and achieve our answer. And again, hopefully those integrals are solvable. Okay, so let's come back over here. So we're going to need a little bit of algebra magic to achieve that. It won't be too bad, I don't think. Let's begin by subtracting x from both sides. So if I have x plus 3y squared, square root of x squared plus 1, dy dx equals to 0. I just copied it. Then I'm going to subtract x, and I get 3y squared square root of x squared plus 1 times dy dx equals to minus x. And now, if I divide both sides by this, or decide to multiply it by 1 over the square root of x squared plus 1 times 1 over the square root of x squared plus 1, then I end up with 3y squared. These guys cancel. This cancels with that. And then I just have a dy dx. dy dx equals to negative x divided by the square root of x squared plus 1. Now I multiply both sides by dx. dx on this side, dx on this side. Then on the left-hand side, these guys cancel, and I achieve exactly what I wanted. 3y squared dy is equal to negative x over x squared plus 1 square root of that whole thing dx. Good. So now if I can integrate both sides of the equal sign here, so let's integrate 3y squared dy. That should be easy. And now integrate minus x over the square root of x squared plus 1 dx. Maybe a little bit more challenging. The left-hand side is super easy. That's just going to be equal to 3. That's just going to be equal to 3 times 1/3 y to the third power. Right? The derivative of this, bring down, cancel. It's gives me exactly that right there. Right? So the left-hand side is easy. The right-hand side is going to take a little bit more work. Let's use a w substitution. So let's let w equal this, which is x squared plus 1. The derivative with respect to x on the w is then equal to x squared plus 1 is then going to be equal to dw dx equals to 2x, which is, well, luckily there's a variable x right there, so that's going to work out nicely. This is going to be 2x dx. Okay, so I'm almost ready to substitute this guy. I'm going to come over here and copy, well, let me copy this whole thing up here. Well, no, I'll put it right here. So this means that so I'm going to put that minus out in front as a minus 1. I'm going to rewrite this as a square root of x squared plus 1 times x dx. So I just copied this and put it over here. I'm just making space for myself. I worked myself into a corner here. And then on the left-hand side, this was 3 times 1/3 y to the third power, right? Which cancels. These guys just give me y to the third power. Okay, now this is almost ready for my substitution. I can see that this portion inside the root will be my w. And I almost have my dw. I'm just missing that too. So I'm going to insert it in here. And I'm going to balance it out by also multiplying it by 1/2. 1/2 times 2 equals to 1. So I haven't changed the value of my integral. And now this entire thing, including the 2, is my dw. Good. So now let me copy this up here. This then is equal to, right, all of that then all leads me to say that on the left-hand side, I just have this y to the third power is equal to, and I'll have this negative 1/2 integral of 1 over the square root of w dw. Right? All of this is my dw, and I have 1 over the square root of w. Okay, let me zoom in here for a little bit. I'm going to rewrite this. Y to the third power equals to negative 1/2 integral of w to the negative 1/2 power dw. And so this is y to the third power equals to negative 1/2 w to the 1/2 power. And then I know that when I take a derivative, so I added 1 to the exponent. When I take a derivative, I'll have a 1/2, so I have to balance it out with a 2. And this will give me that result right there. Okay, so now these guys cancel. And so I end up with y to the third power equals to negative w to the 1/2 power, or this equals to negative square root of w. Now, the w, of course, was this variable we used to substitute. So the w is x squared plus 1. So that means that y to the third power is equal to minus square root of x squared plus 1 plus some constant. Right? Now, ordinarily, we'd be done there, except they give us a boundary condition. So now we get to use this. When, right, that means that the input value is 0. That means when x equals to 0, y equals to 1. Good. So we just substitute 0 for my x, and y gets substituted by 1. So we get blank cubed equals to negative square root of blank squared plus 1 plus c. So I'm going to replace my y values with a 1 from here. And I'm going to replace the x value with a 0 from there. And that helps me solve for c. So this will becomes 1 equals to negative square root of, well, it's just going to become 0 plus 1 is just going to be 1 plus c. Which becomes 1 equals to minus 1 plus c. Or c equals to, add 1 to both sides, c equals to 2. Good, and so now that I get that c equals to 2, I can come back over here and replace the c with the 2. And so I get that y to the third power equals to negative square root of x squared plus 1 plus 2, which, if we flip it around, we get y to the third power equals to 2 minus the square root of x squared plus 1. Looks a little nicer if you can. And finally, we can just easily take the cube root of both sides and solve for y. So then y equals to 2 minus the square root of x squared plus 1, and then the whole thing is being raised to the cube root. So like this, or if you like, you can also write it like this, where we have the cube root of 2 minus the square root of x squared plus 1. I think this one looks a little nicer than that one, but either one is fine. I'm just going to box up this one. Okay, so hopefully that's enough to help you with your homework. Please attempt your homework and stop by my office hours if you have any questions.